So in this lecture, we are going to look at the basics of DC to AC converter, analyze and design DC to DC converters, and understand the principle of voltage modulation in AC. The analysis that will follow can get a bit complicated because you need Fourier transforms to fully understand what is going on. But I'm going to give you just a very rough idea of how we model the harmonics that are generated by this nonlinear system, but I don't expect you to fully understand the concepts behind Fourier transform. That it will likely be covered in more detail in sensors and actuators, sensors and instrumentation. So we're just going to use it here as a tool to get to do the equations we need. And as far as a mechatronics project is concerned, we don't really need to go into the details of Fourier transform. So the equations will be presented more or less for information only. Here is another application. You're going to see this motor later, how exactly it works. And this is a three-phase AC motor. How can you control a three-phase AC motor that we can find in an electric car, for example, if we have a DC power source like a battery? We need an inverter, and now we need a three-phase inverter that can provide a sinusoidal waveform. And each sinusoidal waveform from each phase of this inverter will have to be shifted by a certain amount. And the question again is how are you going to do? We're going to do that. Here is another simple application and very relevant. We have a DC supply that comes from a solar panel, and we want to get that energy that is a DC and inject that into the grid. You know that the grid runs at an AC power. And how to now convert this DC to a high power AC and then inject that into the grid at a very specific frequency. Right? This is another application of an inverter. So let's get started with a simple one here. This is a half bridge inverter. So I'll let you look at this for a minute and try to figure out what is going on here. What is this arrangement? What is this supposed to do? You can clearly see here that it resembles the DC converter that we saw in the last lecture. What is added here? Take a look at it. What is the main difference?
Transistors.
There are more transistors. Now, if we only take this part here, we know how this part works. When the switch is on or the switch is off, the transistor is activated or not, there is a current flowing through the load or not. Notice that in the first stop of this circuit, we have, let's get started from the beginning. We have a source into two, each having half of the input voltage. So our reference voltage here is 0. And here we have positive Vs over 2, and down here we have negative Vs over 2. And the center there then gives us 0. Now let's look at the top branch. If we take this transistor Q1 and activate transistor Q1, then current will flow this way through the load. Current cannot go through this diode because the diode is reversed biased. Current cannot go down because the other transistor is open, and the other diode is also reversed biased with regards to the current voltage input. So when this transistor is closed, transistor Q1, what is the voltage across the load? We are now basically connecting this branch here, and we are applying Vs over 2 to the load. We notice now that the current goes to the left. Now let's look at the other mode. Now let's open transistor Q1 and let's close transistor Q2. Now what is the voltage potential that is going to the load? Is the voltage potential is starting at this point here. And this is negative Vs over 2. When the second transistor is only the second transistor is open, then the voltage is Vs over 2, negative Vs over 2. And where is the current going? Well, now we have the positive potential. Here, this is the negative potential. So according to the convention we used before, current will go like that. Right? Current goes in the opposite direction, as opposed to the DC-DC converter that we had before, where current would only go in one direction. This one goes in two directions, depending on which transistor we choose to operate. When both transistors are open, what is the voltage across the load? That's 0. And when both transistors are on, what is the voltage across the load? If we open both transistors, if they're both fully functional like that, then we are basically creating a short circuit, right? You're creating a short circuit, and the voltage across the load is 0. The voltage across the load is 0. All right, so now we have this mode of operation. Of course, this mode of operation here should not be used. If you want 0 voltage, then use the one where both transistors are off, so no power is delivered to the source. Okay, that's the basic idea. Is the fundamental idea here of operation clear? Yeah. What is the function of those diodes? Why do we need 2 diodes there? The current, according to our simulation here, didn't go through the diode at all. Why do we need them?
To moderate like a certain threshold where the current won't go past.
Well, not really. The idea of having the diodes is to use them as freewheeling diodes. We notice in this mode of operation, we can only operate one transistor at a time. We cannot operate both at a time. We create a short circuit. So in fact, when you close transistor 1 and you have to open transistor 2, we need to give a small time delay. During that interval, both transistors will be closed. If there is any current trapped in the inductor, that current can flow back to the source through the diode. Right? They would go through the diode like that back to the source. So these 2 diodes here act as freewheeling diodes to restore any energy stored in the inductor when both transistors are open. And during the switching, again, there is a small interval between that switching where both transistors are open. Okay. The threshold is still applies, right? But the threshold is not a feature of a diode. It's more like a limitation of a diode, right? Ideally, that threshold wouldn't exist. But it turns out to be 0.7 volts. Okay. Is the video lagging today, or is it better?
From my experience, at least it's been worse than a few other people. There's a part where it just got really, really blurry for like 30 seconds. It was
okay.
But yeah, that's just my experience so far. Still, I really appreciate you going through the effort trying to, make it as best as possible. That's just my experience so far.
Okay, yeah, let's see. If this becomes unreadable, then let me know. We'll try to find an alternative solution. I can just share the screens and then I'll take my image away. Okay, so let me know if that happens. I'll only present what you see here, and then later we go to the light board, and then we'll probably end up going back to Zoom. Okay, so this is the circuit, the same circuit that we had, and here we have the operating mode of each of the transistors. We see that one is open, the other one is closed. Let's call this current flowing through diode 1, through transistor 1, I1, and through the second transistor, I2. And let's plot them right here. This is the steady state current, right? If we let's just neglect this inductor, put that to 0. So our current would simply be the voltage applied to to the load, which is Vs/2 times R divided by R. All right. So when transistor Q1 is on, current flows like that. So I1 is on for this period, and when we now switch to the transistor Q2, then current flows like that, and we have current flowing there, right? Whereas the other current is now 0. So we only have one transistor delivering current to the load at a given time. If you plot them independently, that's what we see. If you now add them up, that's the actual effective load, effective current applied to the load, and that's the result. It's now a square waveform for a resistive load, and that square waveform will resemble this. See, the current now goes back and forth, and the inverter operates, now creates a AC voltage. This will result in a voltage applied to the load that will follow the current for a resistive load, something square like that. But if we had, say, an inductive load, things would be a little bit different because current cannot change instantaneously. So the actual voltage that we would see appearing across the load would be something like that, because of the effects of the inductor that can store energy and send that energy back to the power source. So this would be the effective voltage across the load. It's not a perfect reflection of the current. It would be also not a perfect reflection of the switching input. It has harmonics that we're going to see later. If you now take the root mean square of the output voltage, what is the root mean squared? It's simply Vs over 2 squared over one period, like that. And this gives Vs over 2. Nothing surprising here. What is the average output voltage across the load?
Sir, I have a question.
Yep.
So you said the third graph from the top is I1 plus I2, correct?
No, the third graphic, the fourth, this one right there.
Oh, sorry, yeah, that one.
Yeah.
Well, if you add I1 and I2, wouldn't they just cancel out?
No. If we add I1 and I2, let's look at the beginning here. I1 is positive, I2 is negative. If we add them up, we get I1 up to this point.
Sir, do you mean I2 is 0?
I2 is 0, yeah.
Okay.
So let me clear that up. So here we have I1. When you add a positive I1 to 0, we get I1. Okay, now let's go to the second half of the operation. We are adding 0 to I2. Then we get negative I2 because it's flowing in the opposite direction. All right. So this is coming from the problem that I1 and I2 here are both positive because we are following the way they are defined in the graph. And I0 will have to be positive and negative because current flows in both ways. Right. Okay, so the problem with, yes.
So from,
I'm sorry, I can't hear you.
oh, my bad. So for I1 and I2, they're always just positive or 0. How does it become?
Yes, they are either positive or 0. But you see that I0 here is defined as, what would be that? Let's say I1 minus I2.
Okay.
Because of the way it is defined in the graph. So this graph here would be I1 minus I2. Does it make more sense now?
Are there magnitudes like they're equal?
The magnitudes are equal, yes. They have to be equal because you are applying the same amount of voltage to the load.
Oh, okay.
Okay.
Thank you.
All right, so here is where things get interesting. The actual output you're going to see is not a perfect harmonic or a sinusoidal waveform. It has modulations. It has harmonics that are added to that fundamental frequency. The fundamental frequency in this case would be 1 over the period. That should create a sinusoidal waveform or something square that has the same period. That output is not an actual square or sinusoidal waveform. It has harmonics. If you take a multimeter and you go to your house and plug that in an outlet, you're going to see that you have a fundamental harmonic of 50 hertz, and on top of that, there are small modulations of higher frequencies that are multiples of 50 hertz, 100, 150, 200, and so on. Turns out the only odd ones will be there. The even multiples will cancel out. But there isn't just one frequency, there are multiple frequencies. And the idea of a Fourier transform is to decompose that signal into a combination of different frequencies and different magnitudes. In the same way we had a Laplace transform that was supposed to decompose a signal into exponential and sinusoidal waveforms, a Fourier transform will do the same, but only with sinusoidal waveforms. So this is the fundamental definition of a Laplace transform. This is how we are going to model that curve using a combination of sines and cosines and a shift from the x-axis. Because here everything is symmetric based on the way we are delivering power to the source, then A0 is 0 and AN is also 0. And we are left with sum of B sine of n omega t. So notice here that we have the magnitude B, we have the fundamental frequency, which is 1 over T, the input period, and we have N. N is an integer that will give now multiples of that fundamental frequency, and these multiples are called the harmonics of the fundamental frequency.
Question, sir.
Yes.
So are we just assuming they're odd functions here and no even ones?
We will see that if you do the derivation, you'll see that the even ones will all cancel out because of the magnetic properties of the materials used here, and they don't deform the shape. They don't change much the shape of the fundamental, the overall voltage. They will keep the same, more or less the same shape. So eventually they cancel out. So only the the odd ones remain. So if we are left with this, we can expand that again straight from Fourier transforms. That's the definition of B. I'm going to skip the derivation. You can solve this to get 2Vs over pi times n. N again is the integer that gives the fundamental frequencies. Now take this expression. We can input that back in equation 4, or what is left from equation 4, and we have now our entire output voltage as a series of sinusoidal waveforms. It turns out that for what we need to do, the first harmonic is the one that is actually delivering power to the load, and that's the one you're most concerned with. Ideally, the fundamental harmonic delivers most of the power to the load. The higher harmonics will create alternating magnetic fields that will create in turn eddy currents and will be dissipated in the form of heat. So essentially, the only component of this sum that is actually providing useful power to the source is the fundamental harmonic, that is when n equals to 1. Everything else, as far as mechatronics projects are concerned, are losses, will be dissipated in the form of heat. So for n equals to 1, we can now calculate the root mean squared of the fundamental component of the output voltage as follows. Just to replace n equals to 1, and then take the square root 1 over t of that over a period. I will skip the derivations, but I think you follow what you're trying to do. This is V0 for n equals to 1. Omega is simply the frequency in radians per second. And we can do some more manipulation there, just expanding the equation. And eventually, if you expand the equation and go through all the derivation, this is the result, 0.45 Vs. 0.45 Vs is the fundamental value of the output voltage applied to the load. Not 0.5, as we would have guessed, is 0.45. The rest, the other 0.05 are higher harmonics that don't contribute to the overall power of the system we are trying to actuate. So if you look at the output voltage, it may look like something like the black curve here, like that. We can filter it. This schematic here is a low-pass filter. We can give the input here, this V0 that comes out of the inverter, and you can take V out as the voltage across the capacitor. If we create a Bode plot for this filter, we should see something like this, and this is the cutoff frequency that depends on R and C, 1 over RC, I believe. Right, and if we want this, let's say we are operating at a 60 hertz input, we want to place that is slightly above 60 hertz. So anything up to 60 hertz is transferred to the load. The higher harmonics will now have a lower gain and will not show up in this transformation through the filter. And then you can, yes.
So here, the VR1, that's the actual voltage being seen by the resistor, the 0.45 Vs.
The VR1 is the fundamental component of the output voltage. The resistor sees all components, all harmonics are being applied. But the one that is actually delivering useful power to the load is the fundamental component, which is the one given in equation 10. Right, but everything is seen at the output. If you plug a multimeter there and you look at the an oscilloscope and you look at the output, it will likely be something like that. The fundamental component will be this one. All right.
Okay, thank you.
The second harmonic would be the one with double frequency like that. The third, and so on. Right? But the one that we are actually assuming to be delivering power to the load is the first one, the lowest possible frequency, because higher frequencies here tend to simply dissipate energy in the form of heat. Somebody else had a question. No? Okay. So now let's consider a RL load instead of a resistive load. If you have a RL load, then you can then calculate the impedance. The impedance is simply R plus the impedance of the inductor itself. Now notice that we have here omega, which is 1 over T, and we have also the multiple N, right, that now calculates this impedance for each individual harmonic. For the first one, we would be applying N equals to 1. That is the impedance for the first harmonic. If we now go to the second or third harmonic, then the frequency changes, so the impedance of the inductor for that particular harmonic also changes, hence N applied here. It is relatively easy now to calculate the current. We can simply do the voltage divided by the magnitude of the impedance. The voltage is known from that Fourier transform. So here we have the impedance, and everything else is in this equation is the voltage that we calculated before. Notice that there is a shift here between voltage and current, that is theta N, and that is the angle of the impedance load itself. Right?
Question?
Yeah.
As the frequency increases, doesn't the impedance just become R?
As the frequency increases, the inductor will dominate the impedance. Actually, as the frequency increases, the effect of R will be negligible compared to the effect of the inductor, because N is increasing. All right, so let's say to the 10th harmonic, we would have something like this. It's 10 times higher than what we started with in the first harmonic. So the higher we go in frequency, the more impedance you have in the inductor. All right, so it's actually the opposite. Then the effect of the inductor will dominate the impedance.
So that means like the same way we neglected like the higher harmonics in terms of like useful power, we can't neglect the impedance when
No. Later we'll do that assumption, but just to be consistent, we need to acknowledge that now the impedance depends on which harmonic we are attempting to model. Right? If you're only concerned with the first one, then n equals to 1, and impedance is not dependent on n anymore. And that's what I'm going to do next. So the fundamental output power, see, for n equals to 1, is simply V times I times the power factor here, cosine of the angle of the impedance. That is IR1 squared times R. What is IR1 squared? It's the fundamental output current, because you're looking at the fundamental output power. So this is obtained by setting n equals to 1 here. This gives IR1. And that's the output power. The output current, sorry. So the output current, after some straightforward manipulation, is given here. All right, so this is n equals to 1. And now replacing that in the previous equation, we multiply this squared multiplied by R gives the output power. And higher harmonics, again, are dissipated as heat and do not contribute to the overall power distribution to the load as far as the mechatronics project is concerned. Now, if you assume that you have a perfect inverter, the input power and the output power are the same. Input and output are the same. For high inductance and high inductance and frequency, we have a nearly sinusoidal component, nearly sinusoidal output. So only the fundamental component provides power to the heat, which means that in our equation here, instead of using the actual equation for voltage and current, we can again rewrite this for n equals to 1, because for a high impedance, for a high inductive load, we have nearly a sinusoidal waveform. All right, so replacing that with the fundamental current and the fundamental voltage, we can conclude that the input voltage equals to the power delivered by the fundamental harmonic, the fundamental voltage, and the fundamental current to the load. Vs remains constant, so now the only thing that is constant is Vs. Is depends on the load, so we can isolate for Is by simply taking this integral. That becomes Is times T times Vs. And so for the supply current, this is what we get. Right? Load voltage, fundamental harmonic, input voltage, load current, and cosine of theta, theta being the angle of the impedance for the first fundamental harmonic. Okay.
Question?
Yep.
What would be the average voltage? Like, how would you calculate that?
For the average voltage, we would need to simply take the expression for the voltage here. Where is it? That. Right? We take that at the 1 over t integral of V0 dt from 0 to t. Everything should be symmetric with respect to the real axis, so this should be 0.
Oh, so it's not the same thing with covered where it was like 0.6366 of the.
No,
max.
it should be, because if you look at the graphs and the sinusoidal waveform and a cosine is always symmetric with respect to the x-axis. A combination of them is also symmetric, so the average needs to be 0.
Okay, thank you.
Okay, so what we need to take from all this analysis is that the fundamental component of the current and the frequency is the one that matters to us. For folks working on power electronics, there are people out there whose entire career is devoted to finding the way to minimize the effects of higher harmonics. That's not our job. We don't work with high power and power transmission. We're looking with mechatronics projects. So for us, the fundamental harmonic is sufficient. All we have to take from this analysis mostly is that the fundamental component of the output voltage is 0.45, the input voltage. Now, how do you create a gating signal for this system. Here is one possible way. We have the load, we have the inverter there. This is taking power from an external power supply. And now we have our little microcontroller, an Arduino or something, that whose entire job here is simply to activate each of these transistors. It's not to deliver power. It's only to open and close those switches. And power will be taken from the power input, which is external to the Arduino itself or the microcontroller. So here is one possible combination. We have this arrangement here, and the microcontroller will create this gating signal Q, which is a square waveform that, let's assume it's a Boolean, has a Boolean value from 0 to 1 or 0 to 5 volts, say. When Q is at a high voltage, what happens? Let's say 5 volts. This transistor is at 5 volts. This transistor here would be at 5 volts as well. So the transistor conducts. Current flows from the base that way. So the transistor conducts, which means that this becomes a closed circuit. This also becomes now a closed circuit. The voltage here now goes to 0. There is no current flowing here. Transistor Q2 does not conduct, is open. So the voltage across the load would be, when Q equals to 5 volts or Boolean value of 1, it would be Vs over 2. If we now do 0 volts, then the top one becomes at 0 volts. This transistor now on top is open, does not conduct. This transistor down here is now at 0 volts as well. So it does not conduct, which means that at the base of transistor Q2, we have 5 volts or Vs. Let's put that Vs, assuming that it's 5 volts. And the second transistor here conducts. And now the voltage becomes negative Vs over 2. And again, you see that this is coming from the microcontroller. The entire job of the microcontroller is to provide a low power input to control each of these transistors. And then the actual power delivered to the load comes from that voltage source. That is a DC voltage source, and yet we can get a positive and a negative voltage across the load. Any questions?
So you said this arrangement is representing a microprocessor controlling the output?
The microprocessor is what we apply here. It's either a low or a high output. Let's assume 0 or 5. And this entire schematic here with additional resistor is simply an inverter. We can create two signals that are the complement of each other. If one is high, the other one is low, and so on. In this way, we ensure that only one transistor operates at a time. The main drawback of this is that we cannot have both transistors off, and we may need to do that, right? To have both transistors off, but that will come later. Okay, so that's the principle of operation for a half bridge. Now let's look at a full bridge. Here it is. Now let's take a look at this. And let's see what happens there. We have a voltage input. Again, split into two for reference. The neutral is at the center. Now we have 4 transistors and 4 diodes. The load is at the center. How do we create a current flowing to the right across the load? Which transistors need to operate? Transistor Q1 needs to be on, and transistor Q2 needs to be on. Current will flow according to I0. If we now do Q3 and Q4 while Q1 and Q2 are open, so Q3 and Q4 conduct, now current comes in the other direction. Now, same principle as before. Let's do a deeper analysis here. So let's just look at the first state. Q1 and Q2 are on, Q3 and Q4 are off. What is the voltage across the load? Well, the voltage across the load is always the voltage at A minus the voltage at B. So V load is VA minus VB. What is VA? Well, if Q1 conducts, then VA is at the same potential at that point. VA is VS over 2. And what is VB? VB is at the same potential as this point, which is negative VS over 2. Now, what is V0? The actual voltage across the load is VS, is VA minus VB, and that is actually VS plus VS. Now we have the same voltage as the power source, as opposed to half of the voltage as we had before. Now let's do another mode. Now let's switch it. We have Q3 and Q4 on, and Q1 and Q2 off. What is the voltage at point A? What is the voltage at point A? If Q4, exactly, negative VS over 2, because it is connected to the low potential there. What is the voltage at B? What is the voltage at B? It's positive VS over 2, right? And now when you go VA minus VB, what is the result? Is negative VS. Negative VS. So that's the operation of a full bridge. Now let's do this mode here. Q1 and Q3 are on. What is the voltage at A? Is VS over 2. What is the voltage at B? Is also VS over 2. The effective voltage across the load is 0. You may wonder, why is this useful? We are actually creating a loop here. We are shortening the load. Right? You can actually use this to slow down a DC motor, for example. If you put the terminals of a DC motor connected together and you try to turn the shaft, you see that the faster you turn, the harder it gets to turn, because as you now created a closed loop path for the current that you create by using it as a generator creates itself a magnetic field that will now oppose further changes in the magnetic field, and you create a torque that opposes the motion. It becomes like a damper. This is called a braking or damping mode for a DC motor, when you now short the terminals of it. And you can actually use it to slow down a DC motor, for example, amongst other applications, and restore energy to a power source, for example. So when Q1 and Q3 are on at the same time, or even Q4 and Q2 are on, then the effective voltage across the load is 0. And in this case as well, is the same story, minus VS over 2 minus VS over 2, and the effective voltage is 0. Okay. What happens if everything is off? Then the voltage is also 0, and there is no current for the path. And what happens if Q3, let's say Q3 and Q2 are on? What happens here?
Also
The effective is also 0, but the problem is that we now created a short circuit. We are shortening the input. All right. So you must make sure that the legs are never, one leg is never operating both transistors at a time, right? Because it is a short circuit. Any questions about the fundamental operation of the full bridge? No?
I just have a really quick question.
Yep.
A reminder, how come there wasn't a drop again against across Q1? Let's just say, for example, when Q1 and 2 were on. What kind of resistor are we dealing with again? Is it BJT, or like I just need a reminder, like what's not causing a drop there?
Yes, that depends on the transistor you use, but that's a very good question, because in reality, it's not, you don't see VS in the output. We see VS minus the voltage drops across both transistors. And depending on the transistor, it can be as high as 1.5 or 1.7 volts. So if you're powering this with a 5-volt power supply, be careful. You may not be delivering even half of your input to the output. All right. Especially in low power mechatronic systems, you need to choose an H bridge. This is also known as an H bridge that has a low voltage drop, and that needs to be taken into account. You may have used this before as an H bridge and concluded that it didn't have enough power in the output when you use, let's say, a 9-volt battery or a 5-volt battery. And that is exactly due to the phenomenon that you mentioned. These two transistors were conducting. Each has a voltage drop that depends on the H bridge you're using, and they're taking voltage from the power input. So eventually you end up, so let's say with a 5-volt power supply, you end up with 3 in the actual being delivered to the load. So it is recommended to take that into account when designing this as well.
Gotcha. Thank you. And just another quick question is just a reminder, what kind of transistor are we dealing with again here? Is this a MOSFET? It's not a BJT,
This is a
right?
This is
Okay.
a MOSFET.
I just needed a reminder. Thanks.
Yeah, we don't need a linear transistor. We only need something that opens and closes very fast. Right? So the MOSFET is meant to do that. It's either on or off, and is not really a transistor that operates in a linear amplifier fashion. That's not power electronics anymore. Power electronics is basically a dirty way to do a power amplification. Right? This is not very elegant. We're opening and closing switches, reversing currents, and creating pseudo sinusoidal waveforms in the output. Right? It's not really simply a purely amplification of power as you could do with other types of transistors. But it's so a MOSFET is cheaper and is sufficient.
Great, thank you. That really clears that up. Thanks.
Yeah. So here is the same idea that we had before for the gating sequences. Notice that these transistors here are connected together, so they receive the same signal. They always operate together. The other two transistors are also connected together to the same wire. They always operate together. According to this arrangement, if you create a gating signal Q here that is a square waveform, we are either creating Vs or negative Vs in the output. When Q is 0 or 1, we are operating with one of these pairs always. So this prevents one leg from conducting current at a given time that will create a short circuit. It's the same inverter that we saw before, but now these legs are joined together. How is the resolution so far? Is that fine? Is the lag still bad?
Since the first incident, it's been like not too bad. It's a bit blurry. I think a bit blurrier than usual with what we're usually on Zoom, but it's not like it was before. I can read. Yeah, for myself at least, and I haven't seen anyone else say anything. I don't believe. Yeah.
All right. So should we go back to Zoom for the next lecture? You can type that on the chat. Leave your comment there. I'll look at it later. I think Zoom probably works a bit better.
At least for me, the quality, like the resolution, is slightly less, but the lag is way better. Like you can have the PowerPoint on the screen and yourself. On Zoom, it was way laggier then. Okay.
All right. So yeah, leave your comment there. I will see what to do next. It's not my internet. It's definitely not my internet, and it's not my hardware either. I don't know where this is coming from. I changed the computer. I contact the internet provider, and they said they have the highest upload speed they can provide. So that's done there. It's not my internet and not my hardware. So it must be, I don't know what it is. Anyways, but I'll try to fix that again. All right, so here we can do the same analysis that we did before, the whole thing again, but we'll notice that the only difference is now instead of applying Vs over 2, we are applying Vs. The RMS output voltage instead of Vs over 2 is Vs, following the same procedure as before. The fundamental component that used to be 0.45 Vs now becomes 2 times that, 0.9 Vs. The instantaneous current is the same, except that at this constant, what used to be 2, now it's 4. Everything is multiplied by 2, basically. And there is no further changes. Right? It's the same principle, but this configuration allows us to deliver more power, more voltage to the load. So everything here multiplies by 2.
I think someone's mic's still on, by the way, just a heads up, whoever that is. Not sure. I think someone might be Nor, maybe? There we go. Thanks.
Thanks. This slide is more for reference only. I'm not going to ask you this, how we measure the performance of this switching, but you're going to skip that, so you don't need to worry about this one. It's more for information. All right, so let's do some exercises. Are there any questions about the principle of operation of these systems? Now, is it clear how each of them works? That's fine. Everybody's fine with that. So this can get very complicated. This analysis can get very complicated. There are 2 chapters in the textbook devoted to this, but most of this analysis is for people who actually work on power electronics, and for us, we are concerned with a simple application of this, and everything that it has to do with the fundamental harmonic is sufficient.
I have a very quick question.
Yes.
So you mentioned that there are losses. Was it? So there, in ideal MOSFETs, there might be losses of voltage across the MOSFET. So in real life, would we design like a DC-AC converter in conjunction with a DC-DC converter to increase the input voltage?
All right. So the question is basically, can this? Let me ask this question. What if we just add a duty cycle to one of these gates? Wouldn't that be sufficient to change the voltage level now? If we want to step down the voltage, we don't need to go from 0 to Vs. We can actually, instead of just doing 1 and 0 at a 50% duty cycle, the way we have been doing this, we can actually modulate the output voltage from Vs to 0 by controlling the duty cycle of Q1 or Q2. That's the next lecture. Right, that will come in the next lecture. But if we want now to increase the voltage from a DC power source to something higher than that, then yes, then you need a booster converter first that delivers this, let's say this 48 volts that you see here, and then we do PWM, we do duty cycle modulation in Q1 and Q2.
Okay, thank you.
Yeah. All right, so let's do this one. The following single-phase half-bridge inverter has a resistive load of 2.4 ohms. Determine the RMS output voltage at the fundamental frequency, the output power, the average and peak current of each transistor for a 50% duty cycle, the average supply current, and the last one you're going to skip. Okay, so this is the circuit we want to work with. Is that the one? Yeah. And we are concerned with a number of things. So first, we are concerned with, this is supposed to be the RMS voltage. What is the RMS voltage for this circuit? The RMS voltage would be simply the input, so Vs over 2 times 0.45. Vs being 48 volts is 24 times 0.45. And this is, sorry, first example, first mistake is Vs over 0.45. I'm already accounting for the divided by 2 in the 0.45. So it's Vs times 0.45, which is 48 times 0.45, and this is 21.6 volts. That's the RMS across the load. Nothing complicated here. The second one is the output power. What is the output power of our system? It's simply the load voltage times the load current. What is the load current? The load current is the load voltage divided by the load itself, R. So this is V squared over R. What is V? Is 48 or 24?
24.
24. So 24 squared divided by 10, and this is 240.
Or
Not
is it
240.
2.4?
Sorry, say that again.
Isn't it divided by 2.4?
By 2.4. Yeah, that makes more sense. 2.4 and 240 watts. All right, this is R. Okay. Let's do C. C is the average and the peak current in each transistor for a 50% duty cycle. Now, if you notice so far, what I've been doing is we always had a the bridge on using one transistor for 50% of the time, and then the other one for the remaining 50% of the time. So our duty cycle so far has been 0.5. The question is, given this, what is the peak current and what is the average current through each transistor? So let's find the peak current. The peak current is simply the voltage divided by R, which is 24 divided by 2.4. That's 10 amps. That's the peak current through one of the transistors. Now let's look at transistor, let's say Q1. Q1 conducts for 50% of the time because our duty cycle is 0.5. So what is the average current through transistor Q1?
Is it KV1 or KI1? Sorry.
KI1. Yeah, exactly. K times IP. Well, the peak current, which is simply 10 times 0.5, that is 5 amps. That makes perfect sense. Right? It conducts half of the time for a peak current of 10 amps. Each transistor has an average current of 5 amps. Any questions? No?
Yeah, I have a quick question.
Yep.
Why do we use the resistance of the resistor to find the current going through the transistor?
Because the current going through the resistor is the same as the one going through the transistor.
Oh,
Right?
okay.
Current can only flow here if it's flowing through Q1 or Q2. There's no other path. There are, of course, these freewheeling diodes, but they don't operate with a resistive load. There's no energy trapped here, so these two diodes will never operate. Right? So if there is a current flowing here, it's coming from Q1 or Q2.
Okay, thank you.
Right? If you had the inductive load here, things would be slightly different. The next question is the average supply current. What is the average current through the load?
0.
0, exactly. It's either 10 or minus 10. That's 0. How do you find the average supply? We have IS as the average supply is simply the power divided by VS. Power through the load divided by the voltage across the load, right? If we multiply the input current and the voltage, we have the power. So dividing power by the voltage gives us the supply current, which is 240 watts divided by Vs, 24 volts. And this is 10 amps, which matches the peak current through each transistor. Okay. So this is the peak current. This voltage here is the effective voltage across the fundamental component of the voltage across the load, and that's the power dissipated in the output.
Sorry, question.
Yes.
So the supply current is 10, but the average is 0, or is it just 10 for?
Okay. See, good question. Let me ask this question then. What is the average current flowing through from the load? Sorry. What is the average supply current? 10. The supply current is only in one direction. It's a DC supply. It's
Okay.
a DC supply. What is the average current through the load? Is 0, because half of the time is 10 amps, the other half is negative 10 amps.
Okay.
Right, but what comes from the 48 volts here is always going up because it's a DC supply.
Okay. All right.
Okay. Any questions? No. All right. So I have another exercise that is similar to this one. I'll let you try that one at home. It's the same idea, but it's with a full bridge. If it's a full bridge, what would be the difference? It's the same exercise, same load, but now you have a full bridge. What would the difference be?
Vs is 48 instead of 24.
Exactly.
Sorry.
Vs, yeah. Vs is 48 instead of 24. The fundamental component would be 48 times 0.9 instead of 0.45. And everything else is pretty much the same. So I also asked you about the average of current through each transistor for a 50% duty cycle. We concluded that was 5 amps. What if we had a 30% duty cycle? What would be the average for the last example? What would be the average through each transistor for a 30% duty cycle?
Would it be 3 and 7?
Exactly, it would be 3 and 7 amps. Which transistor does 3? Which transistor does 7? It depends on the arrangement we have. How we actuate everything. But yes, it would be then 3 and 7. Okay, very good. So I'm going to skip this one because it's the same. It's just another full bridge. I want to do something more interesting that is of more use to you. Let's do this thing. Whew. Let's do that one. This is a full bridge inverter. If you go to Amazon and you look for a H bridge, you'll find H bridges there. And if you look at the data sheet, that's what it is for most of them. They'll follow this arrangement. We see here three different things. We have 3 signals: forward, reverse, and DC. Each signal to be controlled by a microcontroller. We have a motor in the center. That's our load. We are operating that motor. And we have 3 different transistors. We have optocouplers, and we have 2 different types of transistors there that operate differently. Let's try to analyze the system and see what are the effects of changing the values of forward, reverse, and DC. DC stands for duty cycle. We'll see how to use that one later. Well, let's assume for now that each of these 3 signals can take a high voltage or 0 voltage. Let's say 5 volts or 0 volts. And let's try to describe how this works based on those signals. This is exactly how an H-bridge works that you can use to power a motor. These are the types of transistors that we have. We have 3 of them. The first one will conduct if there's current flowing in that specific way. If there is no current flowing that way, then it does not conduct. It's an open circuit. The second one conducts if there is current flowing in that specific way. Again, if there is no current flowing that way, then it's an open circuit. And the third one is an optical coupler. It conducts if you apply current through that diode. So the way it works is that you have a source of light on both sides. And when you pass current through one of them, then the other side conducts. But you see the coupling between them, it's not wired, it's through UV or through light. So that allows us to decouple the low power with the high power units. They are not connected anymore. There is simply a light reaction there that will trigger a switch from the H-bridge. And this diode then can be powered from an Arduino or something very low power. Okay, so let's try to do this one. Let's do one example, one, because the rest is the same, and I'll let you figure out. So let's do forward is equal to 1 or 5 volts. Reverse is set to 0. And the reverse is set to 0, and DC is set to 0. All right, so which transistors will conduct? Let's start by looking at this one right here. We have forward 1, reverse 0. So there is current flowing up and through this one and down. So this optical coupler conducts current, which means that this transistor is actuated. If this transistor conducts, then this point here is connected to 0. Right? And the potential there is 0. Potential here is 0, which means that if the potential here is 0 and the potential here is VCC, then current will flow through this transistor and will make this transistor conduct. So if you look here, the transistor conducts if there is current flowing like that. And it is the case here. Again, let's start from the beginning. Forward is 1, reverse is 0. So there is a potential going this way, which will make current flowing this way. So this transistor conducts, which means that this transistor is connected to 0. The potential here becomes 0. We go from VCC through the transistor to 0 current flows. If current flows, this guy conducts. Is this clear? For this specific arrangement, this transistor conducts. So this is conducting current. Yeah? No? Maybe? Any questions before we move on to the next one?
So from the forward, the current is just passing through that light diode and going all down. Nothing is passing through the other one that they're coupled with.
So current passes through the diode up to here, no mystery, which means that this is activated. With this point is now connected to 0 volts there.
Yeah.
Right?
Yeah.
Okay, so the potential here is also 0. Right?
Yeah.
It's connected to 0. The potential here is 0. The potential here is VCC. So current will flow through the diode is the path of least resistance, through the transistor is the path of least resistance, and through 0. So when current flows through it, according to the definition here, this one conducts.
Okay. Yeah.
Right. So that this guy is now conducting. Now let's look at this one right here. Is this conducting or not?
Sorry, question
Yeah.
about the first one again.
Yeah.
So the optocoupler is conducting, so it's like shorting to ground, basically, right?
Yes, it's shorting this to the ground.
So then I understand that. I don't understand how the 0 volts goes past the 1 kilo ohm. Because if this is conducting, but above like the 10 kilo ohm is VCC, it would be like a potential drop across the 10 kilo ohm and then the 1 kilo ohm.
Yes.
Or like where? So then.
Yes. Of course. Yeah, it will be a potential drop here and a potential drop there. But the potential drop here is a lot smaller because the resistance.
Oh, I
1
see.
kilo.
I see.
Well, actually, no. We can't just connect that to the ground to 0.
Right.
We need this 1 kilo ohm there. Because otherwise, if you didn't have this 1 kilo ohm, then you would go from VCC straight to ground, and you would short the transistor, would
Right.
short the power input.
Okay, that makes sense.
All right, so this guy conducts. Let's look at this one here. What is happening to that one? So forward is 1, reverse is 0, DC is 0. Is this guy conducting? Is the optocoupler conducting? Reverse is 0, DC is 0. Both legs are the same potential. It's not. Right? Both legs of this guy here are the same potential. It does not conduct. So this is an open circuit. This is an open circuit, which means that this is floating. There is connected now to 0, because this end is floating. Is this clear? This guy does not conduct because here we have 0, here we have 0. There's no voltage difference. This guy does not conduct, which means that this end here is open. That takes this base and connects that to 0. So no voltage applied at the base here. Now we have a different transistor. We have this type, and this type conducts. Let me get away here. This type conducts if we have current flowing that way. Right? But now we go from 0 to another 0 potential. There is no current flowing that way. This transistor does not conduct.
Question, sir.
Yeah.
Are we ignoring that VCC that is going, that is like right next to that 1 kilo ohm, that right above?
This one, we are ignoring it, yes, because this one is open. It does not conduct. This optocoupler does not conduct. This switch is open. So VCC is not feeding anything.
All right, yeah.
Okay. All right, is this one fine? Did you see that this one does not conduct? Let's look at that one right here. So let's start with the optical coupler. We have forward is 1, reverse is 0. So let me go back here. So this is 0. I think this is 0. This is 5 volts. It's hard to follow on the whiteboard. Okay, there. Okay, 5 volt. Right, correct. Yes, you're right. So this is trying to push current that way, but because of the diode, it does not. And no current can flow this way. So this is open. This guy here is open. Right? We see now that the potential through this diode is reversed. So current cannot flow that way. Can only flow from the top. No current flowing through this means that this is open. This leg is open. If this leg is open, it's kind of floating there, not connecting to anything. The potential here is the same potential as the input. So all this part here has the same potential. This transistor does not conduct. All right, to be able to conduct, we would need current to be flowing this way, right? To be flowing like that. But because both sides here are at the same potential, this transistor does not conduct.
Sorry, sir. Can you explain again right after seeing that the diode is open?
So the diode is open, which means that this end here, this transistor is floating. It's not connected to anything, right? So this resistor can be ignored. We are left with this.
Yeah.
We see that at this part here is connected to VCC.
Yeah.
The bottom here is also connected to VCC. The potentials are the same here and there. Potentials are the same. No current will flow through this path because the potentials are the same.
Yeah.
Right? So if the potentials are the same, no current flows through here. The condition for this transistor, which is this type here, to conduct is that current flows like that. Because it doesn't, the transistor is open, it does not conduct.
Sorry, how is that bottom connected to VCC? The bottom for the 1K?
The base here, this part, this point, the base is connected to VCC through the resistor.
Oh, okay.
Right, that's VCC. All right, let's do this one now. Is this conducting or not conducting? Let's start with this optical coupler here. Is this one conducting or not?
It is conducting.
Yeah.
It is conducting. This time it is conducting. We have a high power to low high voltage to low voltage. So it is conducting. This guy here is conducting, which means that this is now connected to VCC. Right? This closes the switch here, is connected to VCC, which means that the potential here is very close to VCC. The potential at the base of the transistor is very close to VCC. And this other leg here being connected to 0, current will flow this way. Current will flow that way, and this conducts. Current conducts. So now what is the path for the current? The path goes from VCC through this, through the motor, through the other diode, the other transistor, sorry, and back to 0. So what is the effective voltage across the load? Is, because the way we define here, negative, positive, and you're going from positive to negative, it's negative VCC.
So are they acting like a full bridge rectifier with like the diodes, or the opposite ones conduct?
Sorry, could you repeat that? I'm not sure if I got it.
Are these acting like a full bridge rectifier, where when we have like the 4 diodes, the opposite ones are the ones?
No. The rectifier does something different. It goes from AC to DC, right? It has. I see that there's a similarity between this and the arrangement that you use for a bridge rectifier, but they are not performing the same thing at all. So I wouldn't attempt to make any analogy with this and a rectifier.
Okay, thanks.
Okay, so all right, so this and that are conducting. Now V motor is negative VCC. Why negative? Because simply the way we define positive and negative here. Now let's do the same, but let's change DC to 1. If we change DC to 1, we can follow the same steps here. I'll let you do that later, but in essence, the only one that it changes is this one. If we change DC to 1, this one will now go from conducting to no conducting. DC 1. This is supposed to be a number 1. Let's do a North American one like that. If it does not conduct, what is the voltage across the load? The only one conducting is this one. It has no path. Well, what is the current through the load? The current is 0. We can say that the voltage across the load is 0 volts. Okay, so DC 0, negative VCC, DC 1, 0. If we reverse this, forward 0, reverse 1, for DC equals to 1, then these legs are conducting now. And the voltage would be positive VCC. So for F equals to 0, R equals to 1, and DC equals to 0, we would have plus VCC. We now choose these 2 legs with this condition, these 2 legs with that condition. Notice what actually defines what is conducting or not is also DC. When DC is 1, we have 0. When DC is 0, we have negative VCC. What does it mean? This means that this H-bridge, this inverter works like that. We set forward and reverse to 1 or 0, depending on the sign of the voltage we want to apply to the motor. Again, we set forward and reverse to determine the sign of the voltage through the motor. We set duty cycle to 0 and 1 to see if we want to apply that voltage or 0. Now let's make things more interesting and take this DC voltage, this DC value, and make this a duty cycle. Aha. Make this a duty cycle. What do you call this? A pulse width modulation later. So this is T, and this is T1. Now we can have our duty cycle T1 over T. And instead of just giving 0 and 1, give it a duty cycle. Now, in addition to controlling the sign of the voltage, we can control the magnitude of the voltage. We can make it go from 0 to negative VCC in this case, based on the duty cycle. And you can make it go from 0 to plus VCC if we reverse forward and reverse here. So that's an addition to our inverter now. Instead of just doing on-off or plus VCC minus VCC, the duty cycle can be set to this square signal. And now this square signal determines, the duty cycle determines the modulation of the average and RMS voltage across the motor. Is this clear?
So, questions. So anytime DC is 1, the VL will be 0. But then when it's 0, depending on whether forward or reverse or 1, then we'll have a positive or negative at the VL.
Yeah. So let's put it this way. If we have a VCC of 24 volts, I'm running out of space here. So VCC of 24 volts and a duty cycle of 0.5. In this configuration here, what would be the average voltage across the load?
12.
Would be negative 12. Negative 12. If we go here, we now reverse forward and inverse, then it would be positive 12. Now let's do a duty cycle of let's do a duty cycle of let's say 0.75. If the duty cycle is 0.75, what is the voltage across the load? The average voltage across the load for this scenario?
Negative 18.
Negative 18.
Negative 18. So if it's 0.75, okay. So negative 18. Now let's look back here. So there's a trick in this catch here, is that our duty cycle conducts when it's 1. When it's 0. When it's 0, duty cycle is 0, it conducts. When it's 1, it does not conduct. So it's actually the reverse. Just to complicate things a bit more, it's the reverse of this, because the duty cycle is defined as the time it conducts divided by the total period. So we are assuming that this would conduct if when the duty cycle is 1, when this value is 1, the signal is going to 1. But it's actually the opposite, because of this specific arrangement, and it's only valid for this specific arrangement. It conducts when the duty cycle is 0. If the duty cycle was 0%, the voltage across the load would be negative VCC. If the duty cycle was 100%, the voltage across the load would be 0, because it is reversed. So when you do 0.75 instead of negative 18, we actually have negative 6 volts. Your strategy to calculate this is correct, is valid. You say that VA, the average, would be VCC times the duty cycle. That is correct, but there is a trick. The trick is that this arrangement, in this specific arrangement, for some reason, the manufacturer decided that the duty cycle is reversed. It conducts when the duty cycle is 0. So it would be then 1 minus K. 1 minus K. And that becomes the average voltage across the load, 1 minus the duty cycle, right? Everything is in agreement what we saw before, but again, this specific arrangement here is reversed. The duty cycle conducts when it's 0, and in our analysis that we did before, things were conducting when the input signal was high, but now it conducts when the input signal is 0. Hence, instead of negative 18, we end up with negative 6. I just want to show you, based on this discussion that we just had here, how we would actually use this in a microcontroller. Exactly how we actually implement this logic. Let's say for speed control of a DC motor. It's going to be very quick, but I find that this is useful. So let's say we have a DC motor. We are measuring the speed of this DC motor. And you're going to compare this speed with a reference speed. That's the desired speed. This is the error. We put that error in a PID controller, and the PID controller outputs here a reference. Let's call that VRR, a reference voltage to be applied to the motor. You remember how we create a duty cycle before? We can now compare this with a triangular waveform, like in the other lecture that we can create. Right? Remember that this has a magnitude of, let's say, this V, just V. We're going to compare this, and this will give us the duty cycle, depending on the value of this voltage. Now, this duty cycle here is a square waveform. This comparator here will actually give, let's put it this way, the output K is 1 or 0 if this magnitude is greater than V, and is 0 otherwise. So this is not really a sum. Let me remove this. Let's see, we'll put a C here for just a comparison. It's a logic test. If the reference voltage is greater than the carrier voltage, this is from the last lecture, from this triangular waveform, then we set the duty cycle to 1. If not, and you set the duty cycle to 0. So by now moving this voltage here up and down, we are stretching or squeezing the duty cycle there. All right, this is the duty cycle. This duty cycle now goes to the H bridge, or to the, let's call this the DC to AC converter. And this goes to the motor in the form of a voltage. This AC to DC converter takes an external voltage. And what is missing here? What is missing is the direction. Now, do we want this voltage to be positive or negative? The magnitude of this voltage is given by this duty cycle. But now we need to determine in which direction that voltage is to be applied. And how we do that? Well, let's look at the error. Right? Let's look at the error. Or we can look at the magnitude of this voltage here. Now, they'll likely have the same sign. So if we take this voltage, VR, and let's say if VR is greater than 0, then turn the motor clockwise. If VR is smaller than 0, turn the motor counterclockwise. So apply V. If it's counterclockwise, apply negative V. And this input goes to the H bridge. This is Q1, Q2 to the H bridge. You remember the 3 legs that we had like that? These 2 are connected. These 2 are connected. So let's call this Q1, and let's call this Q2. So if you want to apply a voltage in one direction, set Q1, let's say, to the duty cycle, give the duty cycle there, and set Q2 to 0. What does it do? It will apply V. With the duty cycle that we created here, goes in this leg, we are conducting current through these 2 terminals, and you're going with the duty cycle K. If we want to conduct using these other legs, so you're going to apply the same voltage, but now in the opposite direction, then set Q1 to 0 and give the duty cycle to Q2. I think this is not visible. Then give the duty cycle to Q2. Q1 is 0. Q2 is the duty cycle K here. Is this square? Is this signal square waveform goes in here, and you conduct in one way or another. Does this make sense?
Yeah.
Yeah. Any questions? So what are the main elements? Create a duty cycle by comparing the output of your PID controller with a carrier signal. If the output here is, if the reference is greater than this, then set your signal to 1. If the reference is smaller than this, set it to 0. Automatically, as this VR fluctuates, the size here, the duty cycle, will stretch or squeeze. This gives us this signal, square signal, that we now give to the H bridge. The question is, which branch of the H bridge should be taking, should take this signal? This one or that one? Well, now it depends on which way you want the motor to be. So look at your desired voltage. If the desired voltage is positive, choose one. So give one of the signals. This carrier signal, this square signal here, the duty cycle. So now you modulate the voltage here and send 0 to the other one, so it does not conduct. If it is the other way around, you give 0 here and give the duty cycle there. Now the voltage is reversed. Right? And based on the duty cycle, we go from positive, or go from 0 to V in, or from 0 to negative V in, based on the duty cycle that is automatically calculated from the output of the PID controller. Okay, so that's it for today. Any questions here?
I have a question.
Yep, go ahead.
So, in order to do both direction and pulse width modulation, does that mean the triangular waveform would have to go from V to negative V?
Yes, we have to. We can do that, or in this comparator here, we can take the magnitude of VR. It's easier. Just take the magnitude of VR. All right. So even if it's negative, you take the magnitude and then compare to the carrier signal. Now the carrier signal can be only positive, because we are throwing away the sign when you do this comparison, but you are actually doing an additional check here for the direction by looking again at the sign and then determining which way the duty cycle goes. Right? So the sign for determining the magnitude of the duty cycle is not important. We can take the magnitude of VR and then compare that with the carrier signal that goes from 0 to V. And then once that is done, now we determined your duty cycle. The question is, was this positive or was this negative? If it is positive, give it to this branch. If it's negative, give it to the other branch. So we throw away the signal first, but then again, once we determine which branch takes that duty cycle, then we actually have to look back at the sign here. Does that make sense?
So you take the magnitude, and then
Yeah.
that's where you find the how much you want to do your K.
We take the magnitude. So here VR it's always positive. If it's the magnitude, we find the duty cycle from that. Find K. Right? Only based on the magnitude, not on the sign of VR. VR can be positive and negative. Say you want to go at a higher speed, then VR is positive. If you want to go at a lower speed, VR becomes negative. But as far as the duty cycle is concerned, we can treat this as always a positive number and then compare that with the carrier signal to find this. The question then is, once we found this, should this be given to create a positive or a negative voltage? Then it depends on this, because this is your desired output. This is what you want to apply to the motor. In control systems, we jumped from here to there. Right, the output of the voltage here would go to the motor straight, but now we have this logic in the middle. All right, so the sign here depends. The sign here dictates in which way the motor rotates. So the sign here is what determines where this duty cycle goes, here or there. To calculate it, only the magnitude of VR is sufficient.
So it's kind of two comparisons taking place at the same time, one for the magnitude, one for the positive and negative.
Exactly.
And all that happens in the comparator block?
That all happens in the microcontroller. Yeah, in the okay.
Thank you.
So this is useful. I think a lot of you who had projects before use this somehow. But this is how we would treat it for power electronics. Okay, folks, thank you very much. I'll see you again next Tuesday.